Welcome back. Start off with, this video is going to be a little bit long. I got a lot to go over in this episode. So if you want to skip around the boring parts at the beginning, do that. That's fine. I want to start off with a quick update for everybody watching me, wondering where my videos have been. Yeah, job, life, and other things got in the way. That's just kind of how things are. And I have a somewhat limited amount of time every evening to work on my projects. 3 to 4 hours at most, usually. So, yeah, it's not like I sit here all day, every day, you know, in this wonderful, resplendent palace of computers to do things. So, you know, I do things as I have time. On that note, it's actually interesting. Episode 6, which came out not too long ago, I had actually shot that in March, late March. And then things happened. I got tied up with the Coco 2 videos, and then I forgot that I shot it. And I went back to do some research for, you know, this episode and found out that episode 6 didn't exist. So, yeah, sorry about that. When you're, if you want to check up on, if you want to check up on things that I'm doing as I'm doing them, you can follow my Facebook or Instagram. They're up there in the top corner of my page there somewhere. Yeah, I just post little updates and things there. I've also started a Patreon, however that's pronounced. So if you want to drop $1 in the cup and help me keep doing this awesome videos for you, making great content, that would be appreciated, but it's not required. So before we dig into anything further on the computer, now that we're back at that, I did want to talk about the sound options that I did have available. I didn't really touch on that too much on the last episode. Lots of different ways you can add sound to a 6502 computer. One of the options would be one of the AY3-8913 variant chips. You know, I have the 8910s in here. The 8913s have less pins and an easier chip select capability on them to make them a little easy to talk to, potentially. It would require me to use less pins on the 6522 that I'm using to communicate with those chips. However, I've found that the 8913s are both about 4 to 6 times more expensive than the 8910s, and they're harder to get. So yeah, I stuck with 8910s on that. I could have also used the Texas Instruments SN76489, which is very similar in capabilities to the 8910. But the Texas Instruments chip doesn't have independent outputs for each of the sound channels. So it's got 3 channels per chip, just like the 8910 does, but they only come out a single audio output. So if I wanted to do any like special post-processing per channel with those chips, I would not be able to do that. So again, I stuck with the 8910s on that. I could have used like a SID chip from a Commodore 64 and saved myself a lot of headache, because SID chips are specifically designed to talk to a 6502. However, SID chips are insanely rare, and I am firmly in the belief that if there is a working SID chip out there, that SID chip should be in a Commodore 64 or a Commodore 128 where it belongs. So I'm not going to go try snagging up a SID chip that's probably going to be busted or counterfeit anyway for this project. Doesn't make sense to me. I could also just made my own sound generator by using a PIC or an Atmel or any, you know, number of little microcontrollers with just a built-in program to make sound. And then I could have done some really insanely fancy things with that. Like, you know, I could do like crazy sine tone waves and squares and triangles and all that magic. But I wanted to try to stay period accurate. I'm trying to stay period accurate as much as I possibly can for things that I can stay period accurate, and only kind of go off the reservation, off into the bush somewhere for things that would be prohibitive for some reason to implement using the period accurate stuff. Like if I can't get the chips I want reliably or easily enough in bulk, for example, I'm not going to try to use that. I will do some other thing. But, long story short, the AOA 38910s, you buy them online, they're $1 a piece, you buy a few extra, they have a high likelihood of just working, and they're abundant. So it made sense to me. So, on to the machine itself. Changes since the last episode. Let's go ahead and take a look at the board here. A lot of cosmetic changes to start. On the top side of the board, mostly for you guys watching the video, I have labeled all the chips here. So that I know so you can see what every single one of these chips is supposed to do and what its function is. Additionally, let's turn it off there. Additionally, I also did the back side of the board here. All of the chips are labeled here as well. And this is a little bit more for me, actually, so that when I'm flipping the board over and looking at it, I can see, oh, well, that's that chip, that's that chip, that chip, that chip. I know what's what while I'm working on it. I also cleaned up some of the signal wires. This was messy up in here. I cleaned up some of this. This I didn't really get to very much right here, but yeah, I did come through and clean up some of those that were they just happened to be bothering me while I was working on the machine. So what other changes have we done? That's the hardware, so or the cosmetic changes. Let's take a look at some of the software changes, or really talk about them. I made some changes to the monitor program, specifically the subroutine that determines if a character has been typed into the console as a hexadecimal character or not, basically. It was really inefficient and kind of funky. I rewrote that to use just the accumulator instead of using 0-page locations and having to do like explicit compares and all of this other stuff. Basically, we just use the accumulator to pass traffic in and out of that routine. Ends up being a little bit more efficient, and it just tends to work better. And my compare routines, they can come out of when I come out of the routine. I don't have to go check some random 0-page location to check to see if the character is hex. If it comes back and it's a binary 0, it's not hex. If it comes back and it isn't binary 0, then it's got to be a hex character, because that's how the routine spits it out. So it makes it really easy for us to determine what's going on there. I also went through and did a lot of little code improvements, changes to things, and cleaning up the comments and stuff. And we'll take a look at that here a little bit later. So yeah, let's get to the actual demo of the machine here. Let's turn this on, and so you can hear what happened when we turn it on. Let's go ahead and turn it back on, and haha, did you hear that? That little beep sound, does that sound familiar to you maybe? That is the chime sound this guy makes when it turns on now. So on power up or reset, it makes a little chime sound and says, hello. Chime sound's pretty easy. Basically, I set multiple tones on both of the chips and set them with an envelope and just set them to free run and then come back. So the CPU is doing no work, or very little work whatsoever to make that sound. It just says, hey, sound chips, go do it. And they fade out and do the thing automatically, and the computer is immediately responsive upon power up. I also added an error beep. Let's look at the console here. So we look at the console and give it characters. You see that don't correspond to sounds, or correspond to character or commands. I can't think. It complains at you. But if you give it a valid command, obviously it just works. So little cosmetic touch-ups, little details, as they might call polish, just to make the machine a little bit more friendly. A little bit about the chime sound here, that noise. I added a routine to the BIOS itself, or to the monitor. It's really, yeah, BIOS, whatever you want to call it. The startup code, the ROM code, that any program that's loaded on the computer after the fact can use to send sound to the sound chip, so you don't have to have your own sound send routine. It's based on the routine that was used from the music demo in the last episode. but tidied up, cleaned up, and it's more, how can I say, it's more subroutine friendly. It can be used a lot easier in index loops. The first version of that routine passed all of the, you would pass all of the values for what you want the chip to do through the X, A and X registers. But the problem is you'd have to do like funky stuff if you were using X for indexing. You'd have to push and pull it from the stack and do all this craziness, which was dumb. So what I did instead is I rewrote that slightly to use a couple of 0-page locations. So basically what you do is you store the value you're trying to pass and the register you're trying to program in these sound chips up in 0-page, and then just call the routine, and it will go and fetch those values out of memory and then execute stuff as necessary. It makes the code a little bit more difficult, not difficult, longer to use. It's not as space and speed efficient as just using the registers, but it decomplicates stuff quite a bit. You just poke the values in there and then go call it, and it does the thing. Let's get into some hardware changes on the machine. One of the biggest hardware changes to start off with is right up in this area here. As you'll notice, that hex inverter is gone, and I mentioned this on the one of the previous episodes. I was thinking about removing that hex inverter and replacing it with just a simple transistor inverter, and I did that, and it works just fine because the inverter just it inverts this line from high to low when it's active. It goes to the reset pin, which is an active low pin, and resets it. But because this is held for a really long period of time, it's like a half a second really. This doesn't really have any crazy switching characteristics. It's not turning on and off a lot, so the speed of this circuit isn't terribly critical. Let's take a look at what an inverter actually looks like. I'll give you a little computer science lesson, electronics lesson. This is the inverter that I have in place. Taking a look at things, effectively what you have here is a transistor. This is an NPN transistor, and you know NPN because the arrow never points in. NPN. Base emitter collector. What you do is you bring the signal in here and you have to pass it through a resistor, because a transistor will drop as much current as you throw into it, or pull as much current as you want to give it. It'll just eat it all up. So you have to be careful with this. You have to give it a little current limit here, and the same thing on this side. You have to give it a little current limit here. And if you look at the way this is connected, when this is set up, oops, I got something going off on my phone. When this is set up, and there's no current coming in here, the current is going to come in here, and because this is referenced to ground, it's going to pass it out the out as an on as an on level. If we bring, meaning like this is a 0, this will be a 1. If we bring this up to 1, i.e. have voltage on that, it comes in here and it will switch the transistor on. And what happens is, because there is less resistance here than here, it will shunt this voltage this way, and it turns that off, basically. Now, my description of that could be a little wacky, not quite accurate, but it gives you the idea of how the transistor works as a switch. Basically, by turning this on, you're shunting this on and off, which shunts the output on and off in reverse, effectively. So we removed that. Now, why did I remove that? Well, the main thing is cost and complexity. You know, a hex inverter in bulk with the socket is going to be something like 49 cents in bulk for every single one of those that's on this board. However, with this circuit, it's like 6.6 cents, like 7 cents. So it is factors cheaper to build this way. If I decide to ever produce this board, which I've talked about before, I want to keep the cost down as much as I possibly can for circuits that don't need to be that complex. And since that inverter does not need to be that complex, we're going to keep the cost down. However, if you notice right over here, I had to add an inverter chip back in because this is a switching, an inverter that does high-speed switching. So yeah, the thing with this is I'm only using 3 or 4 of the inverters on this. So there are spares, so I can in theory tap this back into the reset circuit at some point and eliminate this. So basically the board is now more expensive than it was before I removed the inverter because I had to put it all back in anyway, but whatever, we'll come back to that. It depends on the board, the final board design stuff. If this circuit ends up being way too far away and it's too complex to get the inversion routed back over here for whatever stupid reason, you know, I don't know. We'll figure that out. Yeah. What else we changed? So no longer do we have this funky, you know, breadboard stupidness hanging off the side of the machine. I went and actually purchased some real headphone jacks. Let me see if I can find one up here. Yep, I should have had these ready, but, you know, I forget things. There we go. So here's one of these. Oops. Ah, I dropped that on the live board and rebooted it. Great. Here it is. This is a incredibly cheap headphone jack. It was the cheapest one I could find, basically, because for this project I just needed something that worked. It didn't have to be like super awesome. It's got a tip ring sleeve, so it's a stereo jack. It also has these like switches. This is one of those that has those little built-in contact switches, so you can send effectively a signal back to the computer to help the computer know if something is plugged in. I'm not using them in this case because it doesn't matter. But yeah, I just tacked that on there. Now the pin pitch and pin width of these sockets is too big and doesn't match my breadboard whatsoever. So I just tacked some wires on here and connected them in here and brought them down through the board and soldered them on the back side. Then to secure this a little bit better, I gooped it up with some hot glue. I don't know if you can see that in there. You know, the red wire, which you may be able to peek down in there, is the right one. The white one here is left. And up under here is the black connection, which is the signal ground. So that makes it a little bit easier for me to, you know, plug things in and out of the computer like that. Okie-doke! So now that we got that, let's talk about the main feature that I added this time around. I talked about it a little bit. I asked for some feedback. People said, yeah, I want to do that. I kind of already decided to do it before I asked for feedback, but the feedback was positive, so we went ahead and did it anyway. And that is per channel stereo panning. I have 6 channels of audio on here, and every single one of these channels goes through a chip up here, which allows me to pan each channel left and right independently. So not only do I have 6-channel sound, I have 6-channel independent stereo sound. I can put them all left, I can put them all right, I can put them all the center, I can put them all anywhere I want by using these chips right up here. The chip that I used was the Microchip Technologies MCP4231- some other blah 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 blah. The reason I used this chip is because it's cheaper. It's something like 72 cents in bulk compared to the $3 in bulk, the other chip I had been looking at. The other chip was, in theory, easier for me to talk to on the 6502 because it had a parallel bus, so I could use some chip select magic with my I/O chips here and turn individual chips on and off and then just send it data. But they were expensive, so I went with these instead. One of the upsides with these two is it has two potentiometers per chip, which means on each one of these chips I can control the stereo panning of 2 channels, so I only need 3 chips to do this. With the other solution, it was 1 pot per chip, so I would have to have 6 chips at $3 a piece, $18, and this is like closer to $3 for the whole thing. Yeah, smarter decision there. It has a very simple SPI interface for programming. Serial Programming Interface is literally what SPI stands for. And allows me to just like stream serial data at it to program it. So basically I can just bit bang whatever at that. I can send it, the pulses, and it does what it needs to do. I'll talk about the SPI a little bit in a moment. It also has 256 values per potentiometer. It's really 257. 256 values per potentiometer. What that means is that I can have really fine-grained control over the stereo. One of the downsides of these chips here is that their volume control only has 15 levels. So when it skips between levels, you can audibly hear it. But with the stereo, it's so fine in its pitch, you can't hear it stepping left and right. So that's a real cool, real good upside about that. It also has the ability to disconnect any of the individual terminal positions or the wiper position of those potentiometers. So potentiometer, is like this, and it's got one end, the other end, and it's got basically this is a big resistor, and this is a terminal A, terminal B, and consider this as a wiper. And as you turn it this way, the resistance on one side grows while the resistance on the other side decreases. These potentiometers can set to where you can just, keep resetting the machine. Here, I'm just going to turn it off for a minute. The potentiometer allows you to, or these pot chips allows you to completely disconnect a terminal so that you can get a fuller range out only one side if you want to. It's got lots of little things like that. You can disconnect the wiper here completely and remove it so that in theory, or in effect, you can almost use the potentiometer as an extra, like a mute control if you wanted to. But that probably won't be used very often, but it's a neat feature to have in there anyway. Some of the downsides of these chips is that these chips do not have a reset pin. So that means if you hit the reset button on the computer to do whatever, because it froze up or whatever, the chips remember their last value, their last potentiometer position. So, if things were slammed hard left and you have to reset the computer, it'll come back up and they'll still be hard left. That means I have to incorporate into the ROM code, which I haven't quite done yet. I have to incorporate into the ROM code a little bit of code to forcefully reset the pots back to center on reset, but that's no big deal. Warning: the following section contains multiple technical errors, partly because I'm still learning, and partly because I'm a dope. Corrections will be displayed in the subtitles below. One of the main reasons why I decided to use these chips, aside from them being cheap, is because they do have SPI. I've been reading a little bit about SPI, the Serial Programming Interface, which is really pretty dead simple. And I wanted a challenge. I'd never done SPI programming before, and I wanted to see if there's a way to hook these up to this machine and make them work without using the standard parallel interface paradigm of these other chips. And I was able to figure it out, so that's cool. So let's talk a little bit about SPI itself and how it works with the potentiometer. So let's pull in the data sheet for this device. That's you don't need that stuff up there at the top. So this is the potentiometer chip I am using right here. It's got lots of pins, and let's talk about the pins. So the pins we're really worried about is, we got ground here and we got voltage there. That's fine, no big deal. The CS pin, chip select, when that pin is low, that means any data that's received on the data pin here is valid data for this chip, and when that's not selected, it's the reverse. It just ignores it. That's very important because the way I'm clocking in data, I am sharing one clock line here and one data line here for all three chips. So if I want to program a chip independently, I got to turn a specific chip on independently. That brings us to these two pins, the S clock and S data in, serial clock, serial data in. Now, this is how SPI works. Basically, you assert the data bit, whether it's a 1 or 0, you assert the data bit that you want on your data pin, then you clock the clock high and then low, or lower and then high, depending on which SPI mode you're in. And for each one of those clocks, it basically ingests that bit. You clock that bit in, you change the bit on your data, clock another bit in, change the bit on your data, clock another bit in. So you just go ding, 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 ding. You just poke it. And that's how you program it. Now, every SPI device is going to have different meanings for what all those bits are going to mean, obviously. And this guy's no exception. He has his own command and data bytes that you have to send it. It has specifications that it has to receive 16 clocks before it takes valid data. This chip also states that the chip select goes low. It has to receive 16 bits, and all 16 bits have to have been received and valid before you bring chip select back high. Then when you bring chip select back up, it actually commits that to the device. There are a lot of other pins here that I'm not using. The SDO, because SPI is designed to connect a whole bunch of devices literally serially, so the SDO, basically when it receives bits on this end, it then clocks them out on the other side. I believe this chip does it 16 clocks later, so that you can daisy chain chips together and almost like a shift register, and shift them out of one chip and into another chip if you want. Allowing you to use fewer traces on the board instead of connecting all the clock and data lines for all of the chips together. You can just chain the data out onto the data in, saves a little bit on board trace, a little bit on board complexity, and then when you want to talk to any chips farther in the chain, you you can just chip select it and do that. I think that's kind of silly. I think it's a waste of resources, in my opinion. So I didn't do it that way. Each chip is individually attached and connected. And I'm not using that pin. The shutdown pin on this it's kind of like a sleep pin. You do that and it shuts the circuitry off so that you can save power on this chip. That's not something I'm really worried about at this stage. And when you put this chip into shutdown, it will also it changes the potentiometer value and disconnects different terminals, which changes the functionality of what it's doing. And I don't want that. And while the machine is on, I want it to be doing its job. So I just leave that float. These pins here are the terminals and wipers. So this is for potentiometer 0. It's got the A terminal, B terminal, wiper. Same over here, A, B, and wiper. So as you change the potentiometer value, as you send it a command to say, this potentiometer, I want to have value 87, it will effectively shift the wiper towards one side or the other of that potentiometer, giving one side more current and one side less current, which means one side gets louder and one side gets quieter. And then what we do is, we would connect the B pins to the left side, the A pins to the right side. We bring our audio input here. We wipe it left and right, and whiz bang, we got stereo audio. So let's show you a little bit how I have these hooked up here. Let's flip the machine over. I say flip it over. So here is how we're doing it. Here's how we are programming and talking to these chips. Right here is the sound via. The sound via has a couple of serial data output ports called CA and CB, effectively. I'm using CB in this case because it has the shifting modes that I want to work with. And it's got two pins. One pin, CB1, sends out a clock, which you can see it's the green wire I got right here. That every time that the sound via sends out a bit, it toggles the clock. And the other one, for each toggle of the clock, it sends out a bit. You can set the via in a mode where in synchronization with the system clock, the phase 2 clock, or whatever you want to call it, it toggles toggle the CB1 line automatically, or CB2, I think I have it backwards, and the other wire, it will clock that data out. You send it a byte of data to the shift register, and then once that data is received in the shift register in total, it will simply clock that data out. Now on the VIA, this effectively almost directly implements SPI, but it's SPI, it's kind of like SPI mode 1, and most SPI chips support an SPI mode 0 or 3 for whatever reason. So in many cases with the sound via here, you can't connect it directly to an SPI device. However, if we look very carefully in this document right here, you can see that this document, or that this chip, supports SPI mode 1. So that means because it supports SPI mode 1, I can connect the my clock and my data directly to those chips and just send the data out, and the chips will pick that data in and just use it. I had anticipated needing to connect these chips up to the sound via in mode 0, and so I built a delay circuit here based on some resources I found online, and I will link them in case you want to look at them. That what it does, it will take that clock signal and it delays it basically half a clock, which then makes the VIA compatible with mode 0. But since I don't need that, I didn't end up connecting it up. Talking a little bit more about SPI mode 0 and 1, basically mode 0 says that the data has to become valid on the data bus before the clock clocks, before the clock comes high. But on sound via, or on the VIA chip, when it's in its standard clocked serial mode, the data becomes valid half a clock late. Effectively, so it doesn't work. But in SPI mode 1, that doesn't matter, because the clock, its expectation of what the clock does becomes inverted, and so because it becomes inverted, the data comes in at the right time, and it works just fine. Well, this delay allows you to use mode 0 because it delays it that half clock. So you could theoretically connect that up and make it work on mode 0. This can be an issue at super high speeds though, and this clock here is not, it's designed specifically for a 1 megahertz system clock, or 1 megahertz bus clock here. So if I were to change the frequency of the computer, this delay would no longer work. In my case, that doesn't matter though, because as you can see, we're clocking that straight out and it just works. So great. I don't have to worry about that delay circuit. These yellow wires right here, you can see we've got them coming up into the inverter, and they come out of purple lines and they go into each of these. These are extra parallel output ports, the PB ports, some of which I'm using, as you can see, as I showed before here, to select the different chip selects for the audio chips, but these right here I'm using as my chip selects for these guys here. In order to make things easy, and because the sound via, when it starts up with all these pins set to 0. They have a 0 output, and as we can see, because this has got the bar over it, these chip select, they turn on with a 0 value. I want to make sure that by default, when you turn the computer on, a 1 value is implied instead. So these come up into this inverter, which I talked about before, and it flips them over to, basically flips them over to 1s, to a positive value to go into these. So on boot, basically, the chips are all inhibited. And then you select the chips by just turning these individual pins on the output, and we'll turn those chips on. Because these pins can be turned on simultaneously, you can, in theory, send the same command to all 3 potentiometer chips simultaneously if you wanted to, but whatever. flip side and backwards like that. So we already heard the startup chime, we heard the error beep, but we really want to get into this thing here and hear how we have stereo audio. So let's demonstrate. I gotta plug all the thingies back in, so you give me just a second while I do that. There we go, the computer is up and running, so let's go over to Sidebench. Hello! So, we got sound output that's working, and we need to send this guy a program. I'm going to send him a stereo test program. This is a program I wrote while I was developing the circuitry to ensure that individual channels and individual potentiometers and their values and everything were working correctly. So let's go ahead and run that. Here we are. I have different options here, 0, 1, ABC. So let's turn on channels. We'll select chip 0. We have a tone there. That's a little loud. Let's turn that down for me. So we have that tone, and then I can pick chip A, B, or C, A, B, C, A, B, C, A, B, C. And then, let's pick channel A. If I hit the space, I will toggle the stereo left and right for that channel. Nifty. So let's check all of them. Chip 0, A, works. B, works. C, works. Let's try chip 1. Chip 1, channel A, channel B, channel C. We have full stereo capability on all 3 chips, all 6 channels. Awesome sauce. But that's boring. I mean, that's not really doing anything fun, so let's do something fun. I made a little stereo demonstration program so we can do something a little bit more interesting than just tones and panning the tones back and forth for you. Wait for this to load. So now we have a stereo demonstration. Let's make some noise. Let's try the sweep here. Pretty neat. It's just the pitch goes up and down while it pans left and right. Let's try the warbler here. Just random pitches sent left and right, toggling left and right, back and forth. Here's one of my favorites, but I'm leaving my most favorite of these for last. The ricochet sound. It's kind of like a gun going off and ricocheting. Nifty. It starts on one side and it ricochets off to the other side. But here's my favorite sound. This is, I don't know what it is about all of these effects I put together, but this one actually sounds like a real effect you might hear in a game or something. This is the passing car sound. That is pretty nifty. It uses a single audio channel, it uses the A channel. That has both noise and tone enabled on that channel. Starts on the one side. I turn the sounds on at a certain pitch, and I let the envelope bring it up to volume. Once the envelope has brought it all the way up to volume, I then sweep both the pitch and the pan, the pitch and the stereo, effectively using the same register value from 0 to 255. Yes, from 0 to 255, which both brings the pitch down, because when you make the number larger for the sound generator, it has to wait that much longer between making pulses for the sound. That's basically how the sound generator works. And also, when you go from 0 to 255, that goes from left, 0 is left, and 255 is right. And so it pans them both simultaneously. Once the pan is done, then it sets the audio on that channel back to envelope mode and tapers it back down, waits for the taper band, and then returns. I love that sound. That's great. So, the computer has basically a fully functional sound system. We've got 6 channels that can do independently or combined noise and tone. with all the cool envelope features that the 8910 has. It's not as cool as a SID chip, but it's good enough for us. And then also now we have stereo panning, something that almost no computer from the 80s had, mainly because you didn't have digital potentiometers back then. But this is a little cheat that I wanted to put in just because I wanted to put it in, and it was easy enough to implement. So let's take a look at some of the code and stuff with this thing. So let's look at the monitor ROM here real quick. I'll show you where I added the sound code. I added, yes, here they are. I added some generic callable routines that are used by the BIOS itself to make the startup chime and the error beep and all of that stuff. But they can also be there for user programs. This one here is clearing the registers. Effectively, what this does is just sits in a loop and it sends 0 to all of the chip registers. Again, I used this in the episode 6 demonstration. But this is a more, how can I put it? It's more loop friendly and subroutine friendly. It uses these 0-page locations here, the chip select, the register, and value locations to pass data to it. And all of the registers it uses, it pushes to the stack, then pulls back so that you can call this routine and never have to worry about any of your values being destroyed, if that's important. There's the chime right there. It's pretty straightforward. It just sets up the pitches, it sets up the amplitudes and all of that stuff, and sends the chime out, basically. It's a programming 1, 2, 3, 4, 5, 6. Basically, I'm using all 6 channels, and I'm doing it's like an F-sharp chord or something like that. It's basically the same chord as the Mac startup sound. And that's why I asked you if it sounded familiar, because it's kind of that sound. Here, let's listen to it again. Nifty! I just like the sound, and I'm a nerd, so I figured I would do that. So that's what that does. Here's the error beep code. Again, it's got that same setup. We set up all the registers, we set the chip to make up all the noises, and then we send the noise out. The error beep does the same trick that the startup sound does, is that it uses the envelope register to control the sound. Instead of having to turn the sound off, wait an amount of time in a busy loop, doing nothing, waiting for it to time out, and then shutting the chip off, it uses a really short envelope. Now, if you listen to this very carefully, it's got like a ting kind of cadence instead of a beep. It's got a ting, kind of like a bell. That's because I'm using that envelope, and the envelope tapers off. But that envelope taper is really short, so it makes a beep noise, but it allows the chip to handle shutting the noise off effectively. So I'm not having to worry about the timing of that. Here's the command, again, modified from what I used in the episode 6 music demo, that we use to send sounds to the chip. Basically what you do is you send to the 0-page locations the chip select, which is the chip you're talking to. It's either 0 or 1, the register value in that chip that you want to modify, and then the value you want to set to that register. And so you just put those in and into those locations, and then this does the magic. Now, because we do have to use the accumulator to push stuff in and out of the via here, we need to, because that's the only way the 6502 moves data around, uses the registers to do that. Again, we push the accumulator out, do all our magic here, then pull the accumulator back in, so that, again, this returns with registers intact. I think every good BIOS program should return with all the registers intact. You know, because if you've done something right, people will never know you've done anything at all. So that's what those programs do. So let's take a look at the stereo demo itself. So the stereo test is kind of boring and short. So let's look at the stereo demo real quick. Pretty straightforward program. We clear the sound chips. I clear this special location I'm using just for this program, which is just my toggle that's used in the warble algorithm to tell whether I'm left or right, whether the last call was on the left or the right, and it's just back and forth. We set up the sound via to be able to clock data to the potentiometers. So what we're doing is we're using the shift mode 110, that's that right there, 110, to the ACR register, the auxiliary control register. And then I'm setting all the pins to outputs just in case. I don't think I actually have to in this instance because it's been done before, but just in case I threw it in there. And what this tells us is that when we send a byte to the shift register in the chip, it will automatically clock it out using mode 110. What mode 110 is, as I've already described it, is it will clock the data out with one of the CB pins, with which I believe is CB2. I could have this backwards, but it uses the one of the CB2 pin as the clock and the CB1 pin as the data, and it clocks them together. So you can use the one pin as your basically your sync to stay in lockstep with the data that's coming out of the chip. And then this is the wonderful asynchronousness of this. When we, just like the sound chip, when we tell the 6522 to send something out on the shift register, we can tell it to send it out and then go do something else if we want to. If we were using IRQ, the IRQ line, I could go tell it to do something and go do something else, and then just wait for the IRQ to come back. And when the IRQ comes back, then I can deal with, oh, well, I was just doing this thing and it's done shifting a byte, so I can go shift another byte. That's the cool thing about that. Also, it's a lot faster. It can basically send stuff out approximately half the clock rate. So this is a 1 megahertz machine. This thing can send out bits at 500 kilohertz, 500,000 bits per second. That is awesome. If I were to try to bit bang this, basically getting my byte, doing some arithmetic to it to strip out the stuff I don't need to send out, and then turn a pin on, and then turn the clock on, turn the data on, turn the clock off, and then do the math again. It would be tens of times slower, easily to do, to bit bang that out. I don't feel like doing that, so that's why we are using that mode. Back to the actual code. So here we have the program just saying hello. It's using the print immediate trick, and just a string of data here, which is what this does. And it just sends that data out to the screen for me, and it's 0 terminated string, so it knows what to do after that. And we go and we get the input, and it tells us whether we're going to do our car, our ricochet, our warble, or our sweep. And then, you know, if there's it, when we're done, we just drop back out to the monitor prompt. So I have to use a jump table. I don't explicitly have to use a jump table. Some of these don't require a jump table, but some of these are too far away for these branches to work. On the 6522, you can only branch approximately 127 bytes away, because it uses a assigned 7-bit offset byte effectively to determine how far back or forward to go. It can't go more than about 127 bytes in either direction. So what I'm doing is I'm branching into these jumps, and then these jumps do a nice far jump out to the actual memory locations. Ricochet here, pretty straightforward. We just say, hey, we're doing the ricochet. We silence the chip. I pick chip 1. I don't have to explicitly pick chip 1, but I am picking chip 1 for this demo because chip 0 in mine, I found that while I was working on it, I must have busted chip 0's noise generator. Chip 0's noise generator is not working correctly, so because the ricochet uses noise, I'm using chip 1 here. But in theory, I should be able to use either chip. We turn on our noise, set the amplitude all the way up, and we start a short, high-pitch noise, a little sound effectively, and then we rest for a tiny bit of time, then we turn that noise immediately back off to make that gunshot sound, the sound, and then we start a little bit of a high-pitched pew noise. We start that, and then for part of that pitch, we're shifting the pitch off to one side, or the pitch down a little bit, while also shifting the potentiometer value down. So what we're using is we're using the Y register as our stereo value. It starts at 0, so it starts at the far left. We're saying, here's the pot chip we want to modify, the potentiometer number we want to change, and then we go and we set that value to that potentiometer. But as you can see, we're also sending the sound value out and then calling sound command. So we're using this same value, the Y value here, as our value, because we're pushing Y to sound value in. This routine just uses Y as its potentiometer value. We're giving it the same value, so it will pan in stereo, and it will change in pitch simultaneously from the same value. And I go here until we've gone through to about 64, just to change the pitch just a little bit, not a whole octave, just a nudge. And then at this point, we set the sound to taper out with an envelope, so it gets quiet, but we're done changing the pitch. So we set that to start tapering out, and then here I finish, see 255, I finish panning it stereo the rest of the way. So it'll make the gunshot sound and the change in pitch off to one side a little bit, then it'll fade off into the other direction. I just thought it was a neat way to do the sound. Then we just wait for a little while the ricochet fades out, and we go back. This is the sweep, pretty straightforward as well. It uses that same trick. You can see right here, we sweep we start with Y, and we're using Y. We sweep it from FF to 0, 0, both the pitch and the potentiometer, so it shifts the pitch up and the pot left. And then we flip it and take it back in the other direction. We shift it back down low and right, and it's done. And it just basically it uses the warble value, or not the warble value. Yeah, it just flips back and forth effectively. It just goes back and forth and back and forth and back and forth constantly until in either part of these it receives your input and then it bombs out. The warbler, this is where we use the warble toggle effectively. Very simple, straightforward thing. It's doing the same thing. It's here it checks to see if we've got input, so it knows to exit. But it effectively right here, it sets a random tone for both the fine tune and the coarse tune. It just sets these random values using a random number generator I found on 6502.org. Smart people out there, thanks. Yeah, that's it. Here I'm using 3 as the range of value for the coarse tune, because if you give it a full FF, it can have pitches that are so low that you can't hear them. So yeah. And then, yeah, we just set this all up. We load the pot value here for the potentiometer based on warble toggle. So warble toggle is either 0 or FF. Effectively, it's either 0 or full. And so this just warbles it back and forth. It's either full left, full right, left, right, left, right, left, right, each pitch, back and forth. And this is just the code to determine whether it's warbled left or right and to invert the value effectively. Passing car! Same old setup. We set up all the things, but like I already said, what we're doing here is we're setting up the car to start with a specific noise and pitch value. Full left, as we can see right here, 0 means full left. And we turn the chip on with an upward taper. So it's tapering from no volume to full volume. So like that, I wait a whole bunch while it does that because I don't want to change the value of the sound chip while it's tapering up. And And then we go with this routine I call pitch cross, that it changes both the pitch and the potentiometer value simultaneously, like I've done before. But it uses a little multiplication math here to do that, basically because I don't want to hold on, what am I thinking? Pot value that better matches the pot scale. Like, I remember why I'm doing this, but I don't remember why I did this. Yes. Yeah, because the pitch value only has like 32 values, and the potentiometer has 256 values, so it's like 1/8. So I do this math here to multiply it by 8 to make the scale of how I'm changing the pitch and the scale of how I'm changing the stereo match, basically, and it's I'm changing them proportionally, effectively. Do it 31 times, do it again, and then once it has shifted the value completely over, then we do the same thing we did before, except with a downward taper instead of an upward taper. And then we wait a whole bunch while it fades out, and then we're done. These routines down here are just basic support routines. I'm not going to get into the random number generator because I don't even know how it works. I just threw the code in there because it does work. But these are the subroutines I'm using. These are just basic REST routines. They're just simple delay loops. The sound IRQ loop. So when you send a byte of data out to one of the potentiometers, if you send another byte of data out to the via to send to the potentiometer before it's done sending the previous byte, it stops what it's doing and sends another byte of data. Really what it does is, no, I was incorrect. It doesn't stop what it's doing. That second byte you send it is lost. It just ignores any incoming bytes until it's done doing the previous byte. And there are usually two ways to handle this asynchronicity. The right way to do it is to have an interrupt handler tied to the IRQ line, because you can set this up, that you set this shift register up that when it's done shifting bits, it pulls IRQ low, interrupts the process, and the processor can then go say, oh, hey, the chip's done doing something. I should do something about that. However, I'm just using a busy loop here because I, to this day, still do not have any of the IRQ lines hooked up on the machine, and I'm waiting to do that until I have a really good reason to use IRQ. So I'll get to that in later videos. So what I'm doing instead is I just sit in a really tight loop, checking the shift register for that bit right there, the interrupt flag register. When this bit goes high, when it goes to a 1, which is what I'm doing with this bit check, that means that the shift register has finished. So I just sit there in a tight loop waiting for the shift register to finish, and once it's done, I can continue what I'm doing. So effectively, this is also a delay loop. This is the set potentiometer. It's pretty straightforward. It selects the pot chip, sends it out to the shift register, and the shift register then clocks that out to the potentiometer that I'm wanting to select. And then I sit in my IRQ loop waiting for it to end. Once it's done, then I send the Y register to the shift register. And that's the Y here is going to be the value that we're sending to the potentiometer. Again, I wait until it's done. Then we release the potentiometer chip because, again, as we remember, we have to bring the potentiometer value for the chip select line low to a 0, send it its data, then bring it back high when it's done, because it will not commit data, or it will not commit its change until you bring the line back high. So we set it low, send the data, set it high, it's done. And that's basically all there is to that. So now we've got full magic awesome sauce. We can make stereo sounds, we can do really cool sound effects. If say we're designing a video game later and we have, something come off one side of the screen and go to the other side of the screen, we can make the sound effects pan with it. Really cool stuff, yeah! Unfortunately, I don't have a fully built sound engine to deal with all this yet. but I'll get to that eventually. A couple other things I wanted to talk about are how I'm loading code into the machine, because I showed, loading code, but I really haven't shown you how it works with my setup, with my development environment. So I'm using the assembler right up here. I'm using the retro assembler by Peter. His last name starts with a T. I'm not going to try to pronounce it. Last time I tried to pronounce it, it didn't go well. But I'm using his assembler, and I'm tying it in to Notepad Plus here. Notepad Plus, I have it tied in with the NPP exec algorithm or exec plugin, so that when I press F6, it brings up this execute function. I can pick the type of output I want and then hit OK, and it will send out a file. His assembler can send out binary files without a header, so just raw binary. And this is what I use to program the monitor ROM. This is pretty straightforward. It just gives me my raw binary file that I then use to program into my programmer right here that I just unplugged. And then I use the programming tool here to send that out. But with these, I use the H6X format. Now, the H6X format is it's a very simple text-based format that has each line with its beginning address of the data on that line, and then the bytes in sequence. It almost looks exactly like an Apple II program listing, a binary program listing. It's crazy. But it doesn't quite match the format what my computer is expecting to receive if you were typing a command into the command line. So I have to do some modifications to that. So I'm going to go ahead and output this. And here is that program. This is the program that I just compiled. And as you can see, it has the raw address and then the bytes of data following immediately after that. And it just repeats in order, 8 bytes, 8 bytes, 8 bytes, 8 bytes, 8 bytes. This is almost, but not quite the format I need. My program, or the ROM here expects all store commands, i.e. a command to place something into memory to start with an S, and immediately have a 4-byte value, or 2-byte, an address value after it. Like that, and then a colon, and then any number of bytes after that, as long as that number of bytes is not longer than the input buffer, which is about 250 bytes long. So, you know, you just put in whatever value you want there. As you can see, that is almost this exact format of this, but not quite. So I created a couple of macros to allow me to convert these fairly quickly into the format I want. The first thing is I need to add my S to the beginning of that, and then a colon right there. So I recorded a macro bound to Control-Shift-Alt-J for Joe that does that for me. So I can just hold Control-Alt-Shift-J, hold that whole thing down, and it will reformat every single one of those lines until I get to the end, and it does it. I also created another macro that simply deletes all spaces in the file because my monitor program does not require spaces between bytes. And if I don't have to be sending those spaces, the faster my upload to the computer goes. So Control-Alt-Shift-Space removes all of the spaces. Now there's one last thing I have to do. This is a plain text file in like MS-DOS format. So it's like carriage return line feed at the end of every single one of these. You can't see them because I'm not showing it in binary mode, but basically every single one of those lines ends as a carriage return and a line feed. However, my monitor doesn't know how to deal with line feeds. I haven't programmed it to deal with line feeds because when you're typing into the console, you're never hitting a line feed button, you're hitting the enter key to tell it I'm done with this command. The enter key is a single character, it's carriage return. So I have to strip all these line feeds out of this. So we do that by doing a replace. Line feed, or a new line as it is, in regex here is backwards n, or \n. So I replace \n with nothing. and it just rips them all out. So I hit replace all, and you see there were 135 of them in there. This file is now properly formatted for JCM-1 to ingest. How do we do that? Pretty easy. So I have RealTerm. This is the program I've been using to send, using it as my command or as my control for the computer, and it has a send function. I set some delays here so that it doesn't send bytes to the computer too fast and lose bytes. I go and pick the file, and I hit send file. And as you can see, it streams the serial data straight into the machine. It's almost like I have kind of a sort of pseudo disk drive functionality going here. Because of this, I can program any program I want and send it right up to the machine. Give it my go command here, go 300. We have a program. So yeah, awesome. Last but not least, I did want to discuss the way I code. So if you've been following me and looking at any of my source code as I'm publishing it up to the website, you really should take my source code with a grain of salt. I write my code to be as easy to read and understand for me as I possibly can, and for you to read as a viewer and understand what the heck is going on. There are 40 quadrillion better ways a lot of my code could be written that could be faster, better, more reliable, using less space, any number of paradigms. But I'm not that smart yet, and I want the code to be easy to read. When I write code, no matter what it is, that's what I always tend for. Make it easy to read first, make it functional, go back and make it faster later, when you're out of beta, so to speak. So that's what we have there. Well, that is it. That is it for JCM-1 today, episode 7. We got stereo audio coming out of this thing, so we have a full hardware engine for audio going. What's next? So I have a couple of different ideas of what I want to do next. One of them is this little thing. A little PIC16F on a Curiosity board that I got that I want to play around with, because there are two major things left for JCM-1 to do. One, that's video. We've talked about that several times, and I'm going to leave it for last probably because it's one of the hardest things to get right. And the other thing is keyboard. I want to do a keyboard. Sorry, I just saw my my amperage on this fluctuate. I wanted to make sure JCM-1 was okay and not frying itself. So anyway, I want to do a keyboard. Now, there are a couple different ways we can do the keyboard. One is to create a PS2 or USB input and shove a keyboard right in there that just works, so I don't have to build a keyboard. And eventually, that's probably what my end result is going to be. Just a PS2 compatible USB port that I can plug any USB keyboard into. There's a gnat right in front of me. You see him? He's dead now. So that I can just do that. The main... Gosh, this gnat. Seriously, am I really that delicious? Go away. Goodbye, gnat. Okay. Insects. So, back to the keyboard. USB keyboard, mainly because that is the most cost-effective way to add a keyboard interface to this computer. However, I do still want to tackle the idea of designing my own keyboard controller and actual physical keyboard. Now, I've shown this before. Let me see if I can get up here and get it. Is it up here? Is it? I don't know where it is. It's there somewhere. Oh gosh, I don't know where it went. But yeah, I was playing around with breadboards and buttons and keys. But that's not going to be the final solution to keyboard input on this for one simple reason. And that is because building a manual keyboard from scratch, even in bulk, is insanely expensive. Any of you keyboard enthusiasts out there who have built your own keyboards from individual key switches, like those Cherry key switches, happen to know that those key switches are something like 45 cents in like bulk of 10,000s? They're crazy expensive. So imagine I had a 100 key keyboard, 50 cents a key. The buttons themselves are $50. It's nuts. I don't want that. That's going to be more than the cost of the rest of the entire machine. That's stupid. I'm still going to design one with some basic, just push button switches. Do I have some of those up here? I can show you. Yep. I'm gonna, use these little keyboard, these little button switches here to make a keyboard. And the reason I want to do that is I want to understand the process and help show the process as well as to what goes into actually designing a keyboard and how the keyboard matrix works. But again, that's not going to be the permanent solution. Well, that's all I had for today's episode. Gosh, it's an hour long, but it's been a fun one. I really hope you enjoyed it. While you're here, check out some of my other videos. Remember, I have a Patreon now, so if you want to drop $1 in the cup, that would be greatly appreciated. That's all I had. Thanks for watching, and remember, 8 bits are all you need.